All right, so thanks everyone for coming to the, I guess this is the first algorithm seminar of the year. Delighted to have Tim Rieder, who is a master's student at ETH Zurich, and he's going to present us some work that got accepted at FOCS, FOCS 2025. So that's it.
Thank you. All right. Also from my side, thank you for coming. So as you can see, this is work done with Maximilian Probst Gutenberg and Erasmus Peng. And just to give you an idea of what we want to achieve in this talk, because it's good to have like a goal in mind, right, when you try to follow along. So we want to find a simple analysis of the random shift decompositions, which we'll introduce later. And they yield two cool results. So first up, that's a tree embedding with expected logn stretch, and an L1 oblivious routing with logn competitive ratio, where both of these results are tight. Okay, and then to start, we will see why these results are actually useful. Okay, so first up, we will introduce tree embeddings. Well, what's that? Well, you've given a graph G, and you want to find a tree that does not have to be a subset of the vertex of the vertices that satisfies these two conditions. So first up, we want that the tree is valid, right? So the tree distances have to be at least as big as the original distances. And second up, we want them not to be that much bigger. So only bigger by an alpha stretch. It turns out that's not an interesting problem to solve. Because there is like easy examples where this alpha has to be order n, for example, the cycle graph Cn. If you remove any edge there to get a tree, then going from U to V from the two endpoints, you have to go all around. So what can we do? We can easily fix this. We just make it probabilistic, right? We still want it to be valid, but the second condition turned into in expectation it should not be that big. And there it turns out that log n is the high bound you can achieve. All right, maybe you've seen already the applications by now, but just to highlight, so any algorithm that you can solve on trees efficiently, you can now solve in log n approximation efficiently, right? Which are a bunch. So ranging from social networks, optimal transport, which gained a lot of traction in recent years, and machine learning, cuts flow and everything.
Hey Tim, can I ask a question? So is this tree need to be a subgraph of the graph, or you can add some new, create some edge that does not exist in the graph?
It's a good question. So I wanted to highlight this actually to compare it to like low stretch spanning trees, right? There you have to be a subgraph. For us, we don't require the edges or the vertices to be subgraph, where the edges are like the thing that actually makes it a new structure. So you can have new edges that didn't exist before. We also allow that you can build on a superset of the vertices, but that you can contract back to the original vertex set like easily with like constant approximation. But the edges is the thing that differentiates it from low stretch spanning trees. Okay. Yeah, good question. Okay. Yeah. All right. And then to look at previous and current work, well, we have the FRT result, which we'll also introduce later, which is the seminal result here. They were the first to achieve the log n stretch, which Bartal showed in the last century that this is tight. And the runtime here is actually from a follow-up paper, but they use exactly the same FRT trees to build a work-efficient runtime. But it's not parallelizable. And then the second version is from Lenzen et al. In 2020. They were the first to make a good parallelizable algorithm. So we have almost linear runtime and almost constant depth, right? But at the cost of having not optimal stretch. And we can retrieve both results. So in the parallel setting, we get the same runtime depth whilst being optimal in stretch, and in the non-parallel setting, we also recover the same runtime.
So the question, the big O tilde for the runtime,
Yeah.
what factors does it hide?
It should hide, so it should be near linear, sorry, not almost linear.
So it hides like polylog?
Yeah, it should hide
Terms.
polylog factors.
Okay.
And it all comes down to doing approximate single source storage paths.
I see. And for the depth, is it also hiding polylog factors?
Yes, there it's definitely hiding polylog factors.
Okay, all right.
Yeah.
So you mentioned if this is not a non-parallel setting, you can still achieve the tilde-OM runtime and scratch is logn, right?
So if it's not parallel, then you can still have just one log. And in the parallel setting, you have multiple logs which come from A as B. So
Okay.
approximate single source
Okay.
source paths.
But the parameter for stretch is always a logn.
That's always logn, yeah. So it's always tight in both settings. And yeah, same.
So you mentioned the lower bound for the stretch is logn. It has been proved. But is there any lower bound for runtime? Oh.
I'm pretty sure logn is runtime. This the lower bound. But I can't cite the source.
Okay.
Yeah.
And where is your confidence? But this makes sense, yeah.
Yeah. And for parallel setting, this is the first to be parallel and tight in stretch.
Right.
All right. The second problem that we want to introduce is L1 oblivious routings. So what is that? You're given a graph again, and you want to find a linear operator A that maps any vertex demand D to a feasible flow F. Okay, and you want to do that for an arbitrary demand vector D, whilst being competitive in relation to the optimal flow that you could do for this demand. So it should be a linear operator that finds a flow without knowing the demand. So for any demand vector D, it has to be close to the optimal if you would know the demand vector D. And you can give this in multiple metrics. And for the L1 oblivious routings, of course, it's the L1 metric that you compare it to.
So, okay, so let me try to understand. It's been a long time since I've seen L1 oblivious routing.
Sure.
So, okay, a special case would be just like ST flow, right? Because then the demand vector D, you have
You have 1, 1, and 1 minus 1.
Yeah, 1, 1, and 1 minus 1.
Exactly.
Okay, so let's say I restrict just the demand vectors of the form 1 and minus 1 and 0 everywhere else.
Yeah.
Then, so it's a linear operator. It maps to a feasible flow. Wait, what? So what is AD?
So it's actually what? So okay, maybe we should discuss this first. AD is so it's just a matrix vector multiplication, right?
Right.
And what you actually do is how to get A in most results is you actually just F is just a combination of the ST flows of D, right?
Oh,
so if you have D given as a 1 and a minus 1, and all zeros are everywhere else,
yeah,
then A gives you the ST flow for this,
oh, right? So
and then F just becomes a summation of ST flows. And it turns out that the summation of ST flows is can become logn competitive if you do the right algorithm compared to the optimal flow that you could find when you know the demand.
Okay, and okay, so the reason this is called oblivious is that you give the linear operator up front, and then
like you're oblivious to the demand.
To the demand vector, right?
Yeah.
And then to realize a specific flow for a specific demand, you apply A to the demand vector, and that gives you the specific flow for that.
Yes. Yeah. Exactly.
Okay, okay.
All right. Again, the goal is to minimize, of course, the commutative ratio. And just to highlight some applications, we can solve transshipment, where here we get, for example, log n or log squared n competitive results. With the Sherman framework, we can use that as precursors to get better results in 1 plus epsilon form of the optimal transshipment. You can do distributed SSSP, and convex optimization also uses this matrix A, use it as left and right profiles.
And SSS single source shortest path, I guess.
Yes, yeah.
Okay.
All right. Again, what do we have for current work? We have the FRT result, and in fact, any tree embedding gives you a competitive ratio already that is tight, or that is the same as the tree embedding. So for FRT, it's tight, but the runtime is very bad. So in theory, you could just take all the exponentially many tree embeddings that you get from the family of trees, right?
Yeah.
You could tell all of them, you can average them out, and then you get a competitive ratio, but you have to compute exponentially many trees. If you want to have the guarantees with high probability, then like taking polynomially many trees is enough, which is roughly what this runtime gives you. And if you want to be better, then this doesn't work anymore. And we can look at a discussion, we can look at how Hoyt et al., how they did that. So they actually only need polylog many such trees, and they can mix better, but they don't get the competitive ratio of log n. And we can again recover both variance, so the competitive tight ratio, and an efficient runtime and parallelizable.
And I guess maybe you were you like what the connection between like distortion and like tree embeddings and oblivious, there's some connection between these two, right?
Yeah, that directly translates.
Okay,
actually. Yeah.
Like one is the dual of the other or something, or
no, it's more of a generalization.
okay, sure.
Yeah. Exactly. So because here you can you can have kind of a combination of two trees, right? And you can kind of say I have this tree and I have this tree, and when I want to route from S to T, I just route half of the flow through the first tree and half of the flow through the second tree.
Oh, I see.
Right.
Okay.
So it's kind of a superposition of multiple trees. That's one way how you can get L1 oblivious routings, and that's how these two results do it. Very high level. All right. Let's look at a few requirements for the main insight and this will directly lead into how we can improve. So first up, we have low diameter decompositions. To recap again, so we do a trade-off between we want small clusters and we want few intercluster edges. So we want to cluster a graph into multiple distinct clusters where few edges go between the clusters, and there shouldn't be that many. But of course, the fewer intercluster edges we have, the bigger the clusters have to be. And these two properties are known to be tight. So this gives you a bound on the number of cut edges. So cut from U to V are not that many. And also the diameter is not that big. And you can see the hyperparameter D, where you can either have bigger clusters and fewer intercluster edges, or you can have very small clusters, but you get more intercluster edges.
Right, so you can get diameter D with cut probability log n, I guess. Log n times the distance.
Yes.
Yeah, I'm just setting D to be like 1 over log n.
Yeah. Okay. How do you do it? Well, the simplest way to actually achieve these tight properties is simple ball carving. We have a graph. We choose a random vertex S. We build a ball with the given diameter. We contract it away, and we continue iteratively until the entire graph is captured. and it actually satisfies its properties. In the following, we look at two extensions of this. So one is a version, actually random shift, that we heard before, and that's the title of the paper as well. That does that in parallel, and it's very elegant. And the second one is FRT trees, where we do that over multiple hierarchies, where we vary this hyperparameter D. Okay.
So here the P refers to probability. I mean,
Yes. Yeah. So first up, we have the random shift paper from 2013. So what we do here is we have a graph. We add a supersource S, and we connect it to all vertices with special weights from exponential distribution. And actually, we make them negative as well. And then we start growing balls from S going to all the vertices. And the different balls, they start at some offset, right? Some negative offset, start growing the balls. And then these balls are captured. And those become then the final balls of the ball covering algorithm. I have an animation for this.
Okay, good. I was gonna
yeah. I showed it before. So here we go. So we have a graph. We add a supersource S. We connect with negative exponential offset. We make them positive just for animation and also if you implement it. Okay, and then we start from there, kind of filling the graph with BFS, and we start growing the balls, and then this becomes its own cluster in the end. Okay, so if you abstract away, this is its own cluster. Yeah.
Wait, so then when do you stop the?
So you stop when
when
all
everything.
yeah, and this is so that's actually like how long does it take, right? So when the last one is reached, that's I believe this one. As soon as this one is reached, then we can stop, right? And reached, you are certainly when this distance of time has passed, right?
Oh yeah, it's
And-
the most that, yeah.
Exactly. So at most, the maximum of n exponentially distributed variables.
Right.
And the maximum, which actually comes up again later, of n exponentially distributed variables is log n times the mean of which is
Yeah, I don't quite get the point that why the green balls, they grow faster than other balls in your
they
animation?
shouldn't.
Could you explain the?
So they just started earlier.
Because I think these super nodes, they have direct connection to every node in the front.
So from S you connect to every node,
Yeah.
and then with some offset, all of them start filling up, right?
Also, the offset is given. I mean.
The offset is you draw them from an exponential distribution.
Okay, yeah, makes sense.
I guess another way to think about it is you grow the ball from S, right?
Yes, exactly.
And then that will induce the small.
So it's kind of BFS or Dijkstra where you just start filling up the entire graph with water from S, and it flows at a constant. Yeah.
Continuous
Constant speed.
extra.
Yeah.
Oh, okay.
Exactly. All right. So what do we recover from the guarantees? Well, almost exactly the same as you wanted for ball growing, except for that the diameters are only with high probability. And this bound, this d times log n, right, that comes from exactly we're log n times bigger than the mean.
Oh.
Right? Because after this much time, everything has been captured. So no ball can be bigger than this. Because the first ball starts growing after 0, and the last ball will stop at d times log n.
Right. Right. The biggest ball has diameter d times log n.
Yeah, at most, exactly. Yeah, because it could start almost at 0 time to grow,
Yeah.
and it will end after d log n with high probability, because then the biggest drawn exponentially distributed variable has finished.
And the first guarantee, how is it?
That's harder to
Okay, sure. Yep.
to like look at, yeah. So second up, we now do this any like your favorite ball carving algorithm you apply now to multiple levels. So how does it work? You pick any ball carving, you apply it to the whole graph, and then you get some clusters, right? And then for each cluster, you cursively apply this ball carving again, but you want smaller clusters. So this the average cluster diameter D, you just decrease it by a factor of 2 in every step. And I don't have a video, but I have a picture for this. So we start with the biggest cluster, and then for each smaller cluster, you recursively go down until you've reached single nodes. All right, that's logn many levels. All right, then we connect the clusters again with edge weights, just the distances between the centers of these. These balls. All right, and because we know that this ball has cluster diameter 2 to the this ball has cluster diameter 2 to the 1 log n. We also know that from here to here, because this vertex is somewhere in here, it's at most 2 to the 1 log n. And then you can bound the distances between all the clusters. All right. So this is actually a tree embedding. So it dominates the original tree metric. So it's a valid tree. All the distances are at least as big. And the expected distortion is low. It's only log n. And again, I can't show you this. It's a seminal result, so it was actually good, right? But I can show you the easier version first, where we show log n squared. And then they tighten it somehow. So let's look at the distance from U to V. And we want to estimate that. So what we do is to get into a bit of details, will help to then see the main result afterwards. So the expected distance from U to V is we sum over all possibilities. You could either be cut in all of these levels. U to V could be cut for the first time in here or here or here, right? Assuming it's cut in here for the first time, then we get a very good bound on the distance. Because we know that this is 2 to 1 log n, 2 to 0 log n, and just adding all of those up, there could be multiple of those, right? It's just a geometric tail. So it's 2 to the L log n in the first level, and then a geometric tail down the line, no matter how long it is. And because of symmetry, the same on the other side. So it's just twice, like 2 to the L log n. Okay? And the 2 to the L cancels with the cut probability for every level. And what we're left with is for each level, we have to pay a log n. And we have log n many levels. So we get a log n squared. And now what they do is, because they know they can bound these distances very, very nicely, and they can fix them, right? When you do ball carving, you can set the exact size of your balls that you want to have. They can cut down on this with the L and reduce that somehow to become constant. And we can do that, but we can cut down on the log n's like here. And let's just say we hope that this works. And we rename this to RL.
Wait, so the goal is we want to replace one of the log n factors with RL.
Yeah, we want to replace this log n with RL. And what we will show is, what we want to have is actually that it's like 1 in every level, or constant. But we can't have that, it turns out. What we can have is that on average, it's constant. That's the goal. And I will show you two like extremes of this and show you why this is the case there. And then it makes sense that everything in between it will also be constant on average. Right. And to continue, like in the next slide, what we actually will look at is the red distances and not the orange ones. So we look at, for a certain vertex V, we look at all the distances from V to the center over all levels summed. And you can kind of see that the red distances will, if you sum them up, they will correlate with orange closely, right? And in fact, this is like by a triangle inequality and the factor 2, this is actually true. So if you want to go from here to here, well, it's certainly shorter than if you go from here back to V, and then from V here, right? And then by triangle inequality, this is just twice. So orange is the most twice the red distances. So let's from now on look at the red distances and look at one worst case idea.
Okay, sorry, what is the red distance again?
That's from V to the centers of all the L-many levels.
From V
So
to this.
V is in every level, right? So every vertex, like in the full graph, you also have some vertex V, and you can look at what is the distance from V to
the center.
the center in every level.
Oh, okay. And then you want to sum all of.
So we want to sum over all these, yeah,
Okay, gotcha.
and then say it's not log n squared, but it's actually log n. Okay.
And you mentioned that this orange distance is almost twice larger than the red distances.
So from here to here, it's shorter than this distance plus this distance, right? And then from here up here, it's shorter than this distance plus this distance for triangle inequality.
Okay, yeah.
You can now from here go back to V, from V go to C2, from C2 go to V, from V go to C3, and so on. And then you need to use every red edge twice. So you kind of go there, then you go back, then you go there, and then you go back. Okay? So it's the most twice. Yeah. Good.
Yeah.
Let's look at this worst case idea, and we have to recap a bit because I think it's quite a big jump to get to this graphic. So what happened here? Visually, I just stretched the graph onto one line. I only care about V, and what is the distance for all the other vertices from V? How far away are they? I don't care in which direction they are. Okay? And then what I just tell you, for me, this is one worst case idea that I had, is, well, let's place them all at distance d times log n away. For we are at level L, and at level L, the mean distance, the mean cluster diameters is dl. So if you place them all at dl times log n away, then we have to pay a lot of this RL. RL is the distance away divided by dl. So you divide by the mean cluster diameter in this level. So actually, you can see this is bad, right? RL will be log n in this single level. And we said it's constant on average. And now we found one where it's log n. So we have to show that in the other levels it's really small. And this is actually the case. But let's recap again, how does it work here? So we have the diameter specified, and then how does the clustering work? Well, this visual, right? You start from S, you start filling up the graph, and they all start growing balls at different offsets. And the question is, who wins V? Meaning, in which cluster will V belong? Is it the case that one of these grows the ball until here and V is in this cluster? Or does V belong to its own cluster? Because as soon as you reach V from S, then S will start growing its own cluster, then S will be its own cluster. If one of those reaches V first, yeah, then the cluster, the distance from V to its cluster center will be dl times log n. right? If it's its own cluster, then the distance is 0. And the bad case is if the cluster center is really far away. So the bad case is if one of these grows the ball so big before we can even start. All right, and this is only the case if the negative offset that I draw in the beginning, if this is really big for this one. So if this starts at minus 1,000 and it's only 900 away, then it will win against V, right? So this is a good time to pause and wonder, like, well, is this true? And I will show you in the next slide how this affects, like if we change DL now. So we can actually look at this over all the distance scales. So this is the original one we had before, the middle one. For smaller clustering diameters, where the mean is smaller, all of these n-1 vertices are so far away that they will most likely not be the center of V. Because you draw exponentially distributed variables, right? But with a smaller mean, so the chance that one of this draws the same, like really big number is smaller and smaller.
Oh, yeah.
And the smaller this becomes, it becomes more and more unlikely that one of these will win a V. Okay, so RL minus 1 is 0 with that probability and so on. Okay, and that holds for all the ones above. They will not win, and V will be its own cluster. What about in the other direction? If we have bigger means, then, well, they will highly likely win against V, but they're not that far away compared to the mean, right? They're only half log n away. And again, you can see if you extend this down, this becomes just a geometric tail. So it's log n, half log n, a quarter log n, and so on. And this is what we wanted to show. We wanted to show that summing over all the RL is actually log n and not log n squared. So it's constant on average. We have a second worst case idea that I won't go into detail, but let's assume the other case, right? We place the same number of vertices on all the distance scales, roughly like n divided by log n for all the log n levels. Well, then we won't have any level where RL is 0, because highly likely one of these that are actually close will win V, and V will most likely not be its own cluster center. But we will never have a case where RL is really big, right? Because there is always, like, no matter what the distance scale DL is, we will always have a lot of vertices that are really close and that are most likely to win V. So here we will have everywhere like a small constant. So we have either like a very small constant for every level, where we like distribute them equally, or if we distribute them all at like exactly one place, then we have one level that's really bad, but then the rest becomes like a geometric tail, and the ones above become 0. And now our assumption is, okay, if you distributed something between like extreme all at one place or like all equally distributed, it is still admits the same behavior. So this is like the thing that we did. This is the formula we picked for this. I will just show it briefly, and if you have questions, we can come back to this later. But basically what you want to do is you introduce this delta L that like measures what is the increase from the previous level to this level in number of vertices that's at a like bad position, right? And it can be if you V here, and then in one level, it might be there are a lot of vertices outside that will induce like a high RL for this level, but then in the future levels, this will be fine again. And then you can have like a big, but for every big increase, you need like an exponential increase of number of vertices that is far outside in like a bad zone, like a certain distance away, that's bad. And like growing the vertices exponentially more, having like exponentially many more vertices than before, at this bad place can only happen this many times. So if there are like a lot of vertices, like exponentially many more than before, at a certain distance away, then we pay a bit of RL in this level, like a non-constant amount, more than constant, right?
So what is B here? The capital B.
Oh, that's the.
This that's like the that's the ball. But that's like not too important, right? It's just from one ball to the next. If you grow by an exponential amount of vertices, then you're allowed to pay a non-constant RL in this level. But that cannot happen that many times. That's basically what this says. So just to show you, you can formalize this idea that anything between like all in one place and averaging them can be formalized somehow. Okay.
Yep.
And I'm close to the end, so we can look what you want to discuss after this. So we want to recap again. So what did we show now? Well, we saw that it could make sense, and it actually works, that you get a tight constant trade-off, not constant definitely, but on average is constant for this distance to center, this RL value. And it immediately implies that you get this 3t with expectation log n, and getting the L1 oblivious routing algorithm is obviously also log n, but you have to use the Heutler result to make it fast and parallelizable. All right, and with this, I would thank you for listening, and I'm happy to take any questions. A few ideas are here.
All right, thanks. I'll just pause the stop the record.